The main purpose of this example is to demonstrate that broadband optical monitoring can provide strong error self-compensation when applied to the production of certain types of optical coatings. A 50-layer non-polarizing shortwave pass, NPSWP, is used as an example to demonstrate this. This filter was discussed in Tikhonravov et al. Optical monitoring of coating production, correlation of errors and errors self-compensation. Proceedings of SPIE 11872, 1-7, 2021. In the File Project menu of OptiLayer, open the directory LEC25D24. Load the 1.52 substrate data file, the 1.45 and 2.35 layer material data files, the design NPSWP, filter 1.4, 52.35, and the non-polarizing short pass filter target data file. Open the T and R in phase window and select Rs and RP reflectance plots at 45 degrees incidence to see its spectral characteristics in a spectral range slightly wider than the target range of 950 to 1150 nanometers. In the monitoring section of the main menu, select the Error Self-Compensation Broadband Monitoring option. The Error Self-Compensation setup window will open. The error self-compensation effect is connected with the correlation of errors by optical monitoring procedure. The algorithm for assessing the strength of the error self-compensation effect is based on a statistical comparison of the effect of correlated and uncorrelated thickness errors on the quality of production implementation of the optical coating design. To obtain a representative set of correlated thickness errors, it is necessary to conduct a large number of computational manufacturing experiments. It is desirable that this number be within a few thousand. Due to this requirement, the error self-compensation option uses its own simplified simulator of coating production instead of the detailed simulator provided by the broadband monitoring simulation option of the monitoring section. In the upper part of the error self-compensation setup window, select broadband monitoring in the transmittance mode at normal incidence. The simplified simulator works quickly, and we can set the number of tests, the number of computational manufacturing runs, to 5,000. In the direct thickness error field, set the value to 0.5 nanometers. This value determines the level of correlated thickness errors generated by the simplified simulator. The higher this value, the higher the level of errors generated. Select the monitoring range from 400 to 900 nanometers with the number of spectral points equal to 501. The last field of the window allows selecting the spectral range in which deviations of the simulated spectral characteristics from the spectral characteristics of the non-perturbed theoretical design will be shown. Select this range as target, the range of the loaded target. Clicking the Run button starts the analysis of the error self-compensation effect. The results of this analysis will be shown in the Error Self-Compensation Results window. The Error Levels tab at the bottom of this window will display the root mean square thickness errors in separate layers calculated from the results of the simplified simulator's computational manufacturing runs. In general, these RMS errors are expected to increase with the increasing number of coating layers, since optical monitoring, along with the positive error self-compensation effect, can also have a negative effect of cumulative increase of thickness errors. In our example, the negative cumulative increase is present, but it is not too strong. The next four tabs at the bottom of the Error Self-Compensation Results window display the results related to the error self-compensation effect. As mentioned above, the evaluation of the strength of the error self-compensation effect is based on a comparison of the effect of correlated and uncorrelated thickness errors on the quality of produced coating. The quality of the perturbed design is evaluated using the same merit function that is used for theoretical designing. Uncorrelated thickness errors are generated as normally distributed errors so that their levels are the same for all layers. And the root mean square norms of uncorrelated error vectors are the same as those of correlated error vectors. This means that statistically, both types of errors have the same level. The total number of uncorrelated errors vectors generated is the same as the number set for correlated errors in the number of test field. The Self-Compensation tab displays a histogram of the error self-compensation coefficients, C, calculated for all simulated correlated error vectors. By definition, this coefficient is the ratio of the merit function variation caused by the correlated error vector to the mathematical expectation of all the merit function variations caused by uncorrelated thickness errors. We say that the error self-compensation effect is present for a given correlated error vector if this coefficient is less than 1 and absent if it is greater than 1. Obviously, the smaller this coefficient, the better. In our case, all C values are significantly less than 1, indicating a strong error self-compensation effect. The C-hat value at the bottom of the window is the mathematical expectation of all C values, called the error self-compensation factor. Note that this is a fairly small value. The Distribution Function tab displays the cumulative distributions of the merit function variations for correlated and uncorrelated thickness errors. By definition, the cumulative distribution is a plot of the probability of having variations smaller than the value indicated on the x-axis. For example, if we choose a variation of 1, then in the case of correlated errors, merit function variations are smaller than this value with a probability of 0.97, 97%, whereas in the case of uncorrelated thickness errors, only 2% of tests give these small values. The fourth tab, RMS deviations, clearly demonstrates the significance of the error self-compensation effect. It displays the corridors of standard deviations of the perturbed spectral characteristics from the spectral characteristics of the theoretical design for correlated and uncorrelated thickness errors. These corridors are calculated in the standard way as root mean square deviations from the theoretical curves. The smaller influence of correlated errors on the spectral characteristics is obvious.